Hey, Chemistry 12 class. Hope everyone is doing well out there and they're being nice and safe. But we are going to be continuing on with our Chemistry 12 lesson in class. It's going to look a little bit differently, of course. And today we're going to be looking at some review. And we are going to also be just doing a little bit of review today. And we might have a little review quiz later this week that I'll tell you more about later. Anyways, here's our first review thing from before spring break. When ionic solid dissolves, it becomes ions in solution. Here we have manganese 2 chloride turning into manganese 2 ions and chlorine ions. But the important thing that we need to take away from here is if we had hypothetically 1 mole of this, it's going to break into 1 mole of that and 2 moles of this stuff right here. So it's going to be a 1:1:2 ratio. So if I had something like this, FeCl3, iron 3 chloride, and it would turn into iron 3 ions and chloride ions. But since it's 3 right here, it would turn into 3 chloride ions for every 1 FeCl3 that dissolves in the solution. So if we started off with a 0.25 molar solution right here, after this all dissolves and it breaks apart, we would have 0.25 molar Fe3 plus in solution. But here it's going to break into 3 chloride ions. So that means it would have a 0.75 molar solution. So if I was to make a picture of this, if here's my iron particle right here, and say if we have like a couple of them, say maybe 3 of them, and we have some chlorines that are attached to this thing, okay, so here's my 0.25 concentration. This is all inside of a beaker right here. What's going to happen is that it's going to be forming this inside of a beaker. It's going to have 1, 2, 3. So this had 3 particles of iron 3 chloride. And now it's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9. These are all mixed up, of course, but it's going to have 3 of these irons in there and 9 of these things. So now it has 9 particles of chlorine, and so that's why its concentration is 3 times as high. So that's some review stuff that we did as well before. Here's some more review stuff right here. Whenever you see this equal volumes of 0.2 molar solution, you don't really need to do any calculations. It just means if you mix these two things together, what kind of precipitate is it going to form if it in fact makes a precipitate. So all of these kind of things are going to be double replacement reactions. So I have AgNO3 plus NH4Br. It's going to be a double replacement. So this NH4 right here is going to combine with the negative ion, this NO3, and Ag is going to combine with this Br right here. Okay, now the next thing is I'm going to look this stuff up, and I'm going to say that AgNO3, well, anything combined with NO3 is soluble, so I'm just going to write aqueous next to this. NH4Br, well, here's Br right here. NH4 is none of these, it's part of all others, and that's soluble. So this is also going to be aqueous, so AQ. NH4NO3, again, NO3 is soluble with everything, so I'm going to write aqueous right here. And AgBr, so Br shows low solubility with Ag, and so this is going to be a solid. I'm just writing this in a different color so you can see that this is our precipitate. we just often write PPT for short for precipitate. So this whole table, remember, comes from your data booklet. And I've attached that into Microsoft Teams, so you can take a look at that. Okay. Our formula equation is just like the equation that we just wrote out. So our formula equation is just going to be your double replacement equation. So I'm just going to write all that kind of stuff here. So PbSO4 plus NaNO3. Okay. And if I looked all this stuff up, it would be aqueous. Okay, aqueous. All this information would come from the table, and this would be our solid right here. Complete ionic equation. So this would be essentially, if all of these are ions, you should show these things in ions. So I would never ask this on a quiz just because, or a test. It would just take up so much room, but it would be essentially Pb2 plus NO3 minus. Since there's 2 right there, this deserves to have a 2 in front. Plus, again, there's the 2 there, 2Na plus, I should be writing aqueous as a subscript for everything here. And then this is SO4. 2 minus. Now, since this is not aqueous, it just stays as PbSO4, solid, plus Na plus NO3 minus. Technically, there should be a 2 in front of here in order to balance the equation, and so that means there should be a 2 in front of here and a 2 in front of there. Okay. Now, the net ionic equation means cancel stuff. So if I was to cancel things, I'm just going to cancel in purple. This 2NO3 here cancels with 2NO3, 2Na cancels with 2Na. And then you're left with your net ionic equation, which would just be Pb2 plus SO4 2 minus turns into PbSO4, and that's our solid. And technically speaking, I should be writing aqueous right here, aqueous right here. Our spectator ions are the things that canceled out. So the NO3 minus is one thing that canceled out, and the Na plus is also something that canceled out. This was the last thing that we learned right before spring break, and it was using this table, which is found in your data booklet right here, to determine how would you separate a solution that had a bunch of stuff mixed in with it. So, so a solution contains Ca2 plus, strontium, and silver, and the idea is that what you should be doing is add one thing that creates precipitate with one thing. So for example, if I decide to add hydroxide into it, hydroxide is not soluble with Sr, but it's soluble with everything with Ag and Ca. So if I added OH to this, it would form a precipitate with more than one thing. It would form a precipitate with two things. It would form a precipitate with calcium, and it would form a precipitate with silver. So if I added, for my first step, adding hydroxide, it would be a bad idea. It wouldn't work, okay? So shouldn't add that. I need to find something that only forms a precipitate with one thing. So what I'm going to do right here is I am going to add, I think, there's a lot of things you could do. There's going to be a lot of different answers. So one answer that you could have is you could have add sulfide to it. Okay, sulfide is not going to form a precipitate with Ca. It's not going to form a precipitate with Sr. It will form a precipitate with Ag. Okay, so adding sulfide as your first step would be a great answer. Okay, another great answer would be any one of these three right here. Again, it does not form a precipitate. It's very soluble with calcium and strontium, but it does form a precipitate with silver. So I think I'm going to add, say, Cl. So I'm going to add Cl to it. I'm going to use it in red color. So I'm going to add NaCl. The Na is just a carrier ion, a spectator ion, just to kind of carry the Cl minus, because you cannot find a bottle of Cl minus. You have to have some kind of spectator ion to kind of carry it in there. So it doesn't form a precipitate with this, not with this either, but it does form a precipitate with that right here. Okay, so your first step would be, step one would be, and this was your answer, this is what you would write for an answer. Step one, add NaCl, okay, to precipitate AgCl. That effectively removes all the AgCl. It would be sitting at the bottom once you do this, and it would be at the bottom of your beaker. The thing is that you do need to get it out of the beaker, so what you should be doing is you should filter that out. So once you filter that out, and I did this demo in class where we had these things mixed together, I filtered it out. I think I wrote fitter, but I think it should be this should be an L right here. After I filter the AgCl, then your beaker only has Ca and Sr. Okay, so now I got to find something that this has been removed from the beaker. I got to find something that just removes one of these things. And I'm going to go back to this one down right here, this hydroxide. It's going to remove the calcium because it has low solubility there, and the strontium is soluble. So if I put in some NaOH, the silver's already gone. Okay, it would form a precipitate with any leftover silver, but the silver has been effectively removed. But I throw in some NaOH, it's going to form a precipitate with this, but not with that. So my step 3 would be add NaOH to precipitate CaOH2. Okay, and as usual, you need to take that out of the beaker. So how you take it out is filter. Okay, so that has been effectively removed from this. Now this is suspended in the liquid, or it's dissolved in the liquid. The strontium, is dissolved into the liquid. So you do want to remove that, and you can just add whatever you want that removes it. So here we see we have SO4 removes it. So I'm going to say Na2SO4, and that does form a precipitate with everything. But calcium is removed, silver is removed, and so we just need to get the strontium out there. So step 5, add Na2SO4 to precipitate SrSO4. SO4 is 2 minus, and Sr is 2 plus, so that's why there's no other subscripts there. And then of course step 6, filter. And that'll remove everything. So this big long step 1, 2, 3, 4, 5, 6 is kind of your answer to this. And that's pretty much where we finished off before spring break. before your online learning. So just a quick review. I think I'm going to have a little mini review quiz on this. And yeah, anyways.